Good afternoon. My name is Raphael Riebl from the Technical University of Applied Sciences in Ingolstadt. And I will talk about handling dependencies to external projects in OMNeT simulations. So what can you expect from my speech today? I will give a brief overview about the status quo of the OMNeT++ build process, and also why it can become insufficient for increasingly complex simulation models. Later on, I will give some basic information about CMake, which is an alternative build tool, and how to combine both worlds, the OMNeT++ world and the CMake world. So when we have a look at the current build process, there's one important tool, OPP which is provided by OMNeT++, which generates a make file specifically for your simulation project. And it uses previously generated make file, which is located in the OMNeT++ root directory, which is created when you build for the first time your OMNeT++ environment. And with that make file, finally your project binary, which might be an executable or a shared object, which is later on run by OPP run. And that process is invoked from the IDE, and then the information is stored in the hidden file OPP build spec, or maybe it's run from a custom make file or a custom build script, as it's done in some projects like OMNeT or Vanes. So even if you say I have never heard before of it, it has also a dialog in the IDE where you can configure all the settings which are stored in the previously mentioned OPP build spec file. Why did I ever bother to deal with CMake and OMNeT++? It all started with a project which first was just some extension classes to Vanes, which is now a separate project called Artery. And it has a dependency on our OMNeT. It's a protocol implementation of the V2X European protocols, which is implemented in pure C++. So it's a little bit similar as we have seen previously from other stacks like PG. I guess that's a similar approach, for example. And it also has dependencies to other libraries. Of course, there are some legacy projects, like I call it legacy because these are non-CMake projects, like Vanes and OMNeT, which of course depend on OMNeT++ itself. And of course, Artery might have classes as well, which depend on C-simple modules, so they also have a dependency on OMNeT++. So how can we integrate it into CMake? Fortunately, that stack is already a CMake project, so it's plain simple to integrate in any CMake project. And CMake itself has a mechanism which is called find package. It's a command in the CMake toolbox. And it has already built-in support, for example, for boost libraries. And you can easily create and extend this mechanism for custom libraries when it's not officially yet supported by CMake. And actually, you can handle the OMNeT++ itself like any other ordinary C++ library as an external dependency. Because OMNeT++ has also an include directory where the header files are located, and there are some pre-built libraries which are linked to your simulation model. Then these OMNeT++ legacy projects are a little bit harder to integrate into this CMake project. So how can we actually do that? That's the main issue actually if you want to integrate it in the CMake environment. So why CMake at all? CMake is nowadays widely used for a lot of C and C++ projects. So it's a pretty standard and widespread tool. And it also offers a convenient user interface to configure your build process, to change compiler flags, make debug builds, relays builds, different optimization levels, and it also handles dependency quite nicely. So as you've seen before, this boost dependency or other libraries installed on your system, but it varies from system to system where it's really installed, and that can be handled quite easily through these CMake mechanisms. And it also handles internal build order of various targets. So if you have a shared library which is used by several sub-libraries in your project, then that one is built at first, so other internal dependencies can link to it. Compared to make files, which has a rule-based syntax, most people consider the syntax of CMake much more accessible. It's easier to read. It looks a little bit like, well, an ordinary script language. And last but not least, I had previous experience for CMake, so it felt like a natural choice. So I suppose not everybody is familiar with CMake yet, so I give some basic information what it is and how it works. The CMake project has at least one file located at its root that CMake lists txt, which includes this script language. It's written in that specific CMake script language, which defines the executables and libraries of your project and how to build them, which source files are needed to compile the binary. And there are also the dependencies between all these build targets and other libraries located on your system is defined. The overall build process of CMake consists of 3 phases. The first one is configuring a build directory where CMake cache is located, and that CMake cache stores all the locations to your external libraries, for example, where the include headers are located for these libraries. There's also stored what's the build type, if it's a release build or a debug build, which compiler flags have to be set. Also which compiler to use at all. You can switch compilers. That's all in the build directory. Then CMake generates for a native build tool out of this configuration specific build files. That can be ordinary GNU make files. It can be for Ninja, which is another build tool, or it can be Eclipse project files. It can also be Visual Studio project files. They have a quite extensive set of supported, they call it in CMake generators, where they support these tools. And finally, well, the actual building process using one of these native build tools. So when we want to use CMake for OMNeT++ simulation projects, there are several steps. First of all, this find package mechanism of CMake has to be extended to find OMNeT++ itself. So the include directories of OMNeT++, the pre-built libraries, as well as some compiler flags which are stored in this previously mentioned makefile.inc in the OMNeT++ root directory. And for example, there's also an OMNeT++ message compiler which might be needed to invoke part of the build process to generate out of these message description files real C++ code. But that's actually the easy part of the whole thing, because these scripts are written for every non-widespread libraries. So Boost, for example, is built in, but more exotic libraries like the previously geographic lib, you have to write it yourself. That's not that complicated. Furthermore, you have to integrate the existing OMNeT++ project in your CMake project. So if you want to use in your simulation model, for example, ENet or Vanes, or I don't know what, we have already heard of several when you want to integrate these and reuse in your project, you want to avoid making changes to that project because it's maintained by someone else. And the solution should be somewhat generic. So, of course, you can write code which works perfect to integrate, let's say, OMNeT, but doesn't work for any other project. Ideally, this approach should work for, let's say, most OMNeT++ projects. Last but not least, it should be easy to use. If it requires a lot of code to integrate it for each project, well, I guess nobody wants to use it. And the last step, we also need to support some OMNeT++ specific features, namely these network description folders. So when you want to run your build library, you have to, for example, use this OPP run binary, which is shipped by OMNeT, and have to pass where these net folders are located to run your actual C++ code. That's a runtime requirement. And therefore, I've extended this CMake mechanism. It has so-called properties which can be assigned to targets to support net folders. And so these net folders are inherited to the upper target. So it knows about all net folders from all its dependencies, and you can assign these net folders to the OPP run target. So how does it look like? This find package mechanism is usually extended by providing a find OMNeT pp CMake file. So it's always find and then name of your argument to the find package mechanism in the CMake extension. And it has to be located in the CMake module path, so it can be found by CMake, and you can set for your project this module path to a subfolder, for example, of your project, so it can easily find custom tools. And as I've said, you can basically treat for that case OMNeT++ like any other C++ library. Some specialties you can do some lookup heuristics, because usually the OMNeT++ binary itself is somewhere in the path environment variable, so we can have a good guess where this OMNeT++ root directory is, and furthermore then consequently the include directories and where the libraries are stored. We have to extract some data from this makefile via regular expressions, which we can then add to these targets, to imported libraries, and add to our build process, so compiler definitions are set properly. And we have dedicated libraries with debug symbols in that OMNeT++ directives. There are actually two types of libraries. One with I guess it was a D suffix for debug. So if it's a debug build in your CMake project, you can use automatically the debug libraries of OMNeT as well. So just as an example, what these generated make files from OPP make look like. Fortunately, they include some information how it was invoked originally. So it doesn't matter if it's invoked by the IDE or by a custom build script. It always has information, well, what's the name of the binary, where in which output directory it's stored, what it is. So here it's a shared object. Compile definitions which need to be passed, so it's interpreted correctly during compile process, where the include headers are located relatively to this makefile. So that one is in OMNeT source makefile, so one step up and then it's in the source directory. And that information can be used for this import process using legacy projects in CMake projects. And that's done by parsing that line and interpreting what it does mean, these flags. That's done by a script I call OPP-CMake. It's a Python script for now, which understands that syntax and can create a proper CMake file which imports the previously built libraries of that legacy project as CMake targets, so they look like ordinary CMake targets from then on. So if you have a look at the build phases, what's happening. So we have one legacy project which is using the OPP make and creating a make file, and then we have a legacy binary, libinet shared object, for example. Then during the generation phase of CMake, OPP CMake is invoked. It reads this header line of the make file and generates a target file with the imported targets, which then can be used by during the build phase from a macro import OPP target, which just includes that one. So these targets are available in our build phase. We can compile and link our simulation model with the legacy binary, and then have our new project binary, which has a dependency on the old OMNeT++ model, which has no idea of CMake at all. And I want to give a little example that it's not that complicated to use, actually. So the first lines are pretty basic of any CMake project. We define a name of our project. We set which CMake version we need at least. That's the line we have told that we can define the module part where it can look up this find OMNeT pp CMake file. Then we use find package. Okay, you say I want OMNeT pp and at least version 4.6. That's an absolute requirement, it's not optional. So if it doesn't find OMNeT++, then just fails during this generation phase, and user can fix that error, for example, by providing the exact path to the OMNeT++ root directory. And here I've, for example, included the OMNeT model as a dependency for that project. I look up a path where somewhere is a source OMNeT package net description file, so I can identify that it is really an OMNeT directory and not something else the user is hinting at. And I say, okay, when you import that target, it should be available as OMNeT target, so I can link to it later on here. And its make file, which I have to pass, is located at OMNeT here, which is just read here as a CMake cache variable. And during this import OPP target, that one also handles the invocation of this OPP CMake script automatically. So the user actually don't need to deal with this script. It's all handled by that one call. And then we build our own library under some sources, and it's a shared library set the target property that it has a net folder. It's located in source where these package.net files are and all these network descriptions for our particular modules A and B. And then link it with OPP and OMNeT, and finally add a run target, which is called run project, which means we can, if we use make files, we can just run make run project, and it executes our simulation model automatically set with all the necessary net folders from our project itself and also from all the net folders of OMNeT. And it should use a simulation configuration file at that particular location. So these presented scripts, because it's a little bit fast to understand all of it right now in the presentation, are available at GitHub. Also with the Artery project. So I have a specific branch of Artery where I show the usage of all these scripts, so we can actually try it out and it really works. And I suppose it might be usable for some of you which also have complex setups. I experienced in the past when Artery started, we used Wayne's configure script, which is a Python script, and extended it a little bit. And well, at one point you reached, well, if I extend it a little bit more, then I have more or less a CMake clone, and I don't want a clone of CMake, so reuse CMake. And of course, if you have feedback to that tool and maybe some features are missing yet for your use case, well, I would love to see some maintained version of that tool at the central place. I don't like the idea that it's fragmented over several places, like I guess this energy framework suffered from. So yeah, maybe it's useful for you. Thank you very much.
So let's Raphael. He was on time, so there is still a few minutes for 2 questions. Does anybody have a question?
So I like CMake too, so I'm a big proponent of that. You still have OMNeT that's going to be compiled. If you're on Windows, you still have OMNeT compiled with MinGW, so the libraries created are still MinGW libraries. So if I have other pieces of software that I would like to link with an OMNeT library, I have to compile with MinGW, otherwise it is not going to link.
Yeah.
I don't know, this might be like a more general question, is there been any look at just saying OMNeT itself could have a CMake list file that can compile OMNeT using Visual Studio or MinGW or
sure, that would be
of
nice.
other tools.
But I guess
so
that's
I had this in the forum, so we kind of.
Yes, that's something that we have been also contemplating. As a first step, OPP MakeMe could have a CMake alternative, but this is something that you implemented as well, no? Isn't it?
No, actually, I didn't change anything of the OMNeT++ build process of itself.
Okay.
It's more
You just
glue code to adapt legacy OMNeT++ projects and make it available into CMake projects.
Yes. So actually we are quite new to CMake, so we are gathering experiences and then we'll see.
Yeah.
OMNeT projects have this feature called features, where you can define subsets of models. Do you concern these features also? Because that's something that's really difficult for us. We are mixing a lot of different frameworks, and we have dependencies in the features, so that a feature in one framework requires a feature in another.
Well, currently I don't build dependency projects. So if you are using, for example, OMNeT, which has these various features enabled or disabled, it has to be built beforehand. So I'm just passing the previously generated makefile, and it has already to be built in that directory by this ordinary makefile. I just import it, but I don't build it, at least currently.
So that would be a...
But you could, for example, check if certain compile flags are set via CMake. So you could test if that particular build of OMNeT has feature X, Y, Z enabled or not. And if not, it's a requirement, you could just emit an error message and hit the user particular, but you have to enable that feature and recompile OMNeT. Yeah.
Are you supporting version checking for external dependencies? Because that trips up many of our users. They download an old version of OMNeT and try to link that with their project and everything, of course.
Not yet. Currently it's only for OMNeT++ itself, the version checking, but it could be integrated without big issues, I guess. At least if they follow a common scheme how to check the version. For example, in OMNeT there is a file where the version number is included.
Yeah, I think that changes from OMNeT version to OMNeT version, where the version number is.
Yeah, great to hear that. But if there is a mechanism to determine the version reliably, that could be integrated, yeah.
Thank you.
So, thank you very much. Thank you.